Okay. Right, so let's start. Today I want to start talking about relativity. Basically, the goal is to explain why we need a new theory, like a special theory of relativity, and to understand how it modifies the existing theory. The existing theory is Newtonian theory or Galilean theory, and we are going to see why it does not work for at least speeds that's comparable to the speed of light. So I think I want to start with let me first start with something called time dilation. And to understand this, I need to first tell you the postulates. Like previously, we mentioned that there's there was a expectancy of a medium that's called ether, and it had some problems, and the requirement came from the Maxwell equations and the form of Maxwell equations. They were obeying certain symmetries, and these symmetries also they were obeying some wave equation, and when there's a wave equation, we were expecting a kind of medium, which was ether. And then the experiment was done by Michelson Morley, and then they couldn't find any ether. So Einstein came. Okay, before Einstein, there were people like Lorentz, Poincaré, I don't know, there are other people, Minkowski, maybe a little bit after Einstein. But I will start with Einstein, and Einstein started with two postulates. So Einstein had two postulates. The first one was laws of physics are the same in all inertial frames. So an inertial frame is the frame in which Newton's second law, maybe Newton's first law holds, like things moving with constant velocity is going to keep moving, things that are at rest are going to stay at rest. If you observe this law in your frame is an inertial frame. And Einstein said, there is no choice between different inertial frames, right? Like maybe you are conducting your experiment on Earth, maybe you are conducting your experiment on Mars, maybe in Andromeda galaxy, maybe you want to conduct an experiment in a plane. As long as you are in an inertial frame, it doesn't matter. Laws of physics are going to be the same as long as you are in the inertial frame. This was the first postulate, and the second postulate was the speed of light. Speed of light. I'm going to use c for speed of light, is the same in all inertial frames. Okay, this is all. Whatever the inertial frame is, the speed of light is the same. Now, when we state these rules, these postulates like this, they may not look very absurd to you, but the second one is especially absurd if we are used to the universe of Newtonian mechanics. And let me demonstrate that before I proceed. Suppose we have a train, and train is going with some velocity v, and suppose we have two observers. One observer, let me call this observer A, is at rest. I'm going to call it rest, but at rest with respect to who, right? Rests with respect to its own frame. So who is moving with respect to who is a little bit, right? So we are aware of that. And according to observer A, the train is moving with velocity v, and inside the train there is another observer. Like, let me call this observer B. Of course, according to observer B, A is moving in the opposite direction. We know that, simple stuff. Now suppose there is like a light source inside the train, like suppose like there's like a laser flashlight, something like that, and it shines in all directions. And this observer B can measure the speed of light. Right? And he or she is going to find the speed to be c, right? In R, it's like in her or his frame, speed of light is speed of light. What else can he or she find? But now, according to A, right, the question is, what is the speed of this red light with respect to A, right? What does A see? And like before we think about light, we can think about classical physics, right? I want to think about, for example, Usain Bolt running inside the train. He runs 100 meters with something like, I don't know, 9.8 seconds, maybe 9.46 seconds if he does his best. And B is going to see this world record. But if A is looking Usain Bolt running from outside, Usain Bolt runs with what he runs, but there's also the train speed, right? He's going to like cover more distance because the platform is also moving. And so this is what we call, according to Galilean physics, we are going to talk more about this Galilean velocity additions. A will see what? Right, simple high school stuff, right? High school physics starts with things like this. What will A find? There's like C and there's V, huh? Exactly. So C plus V. This is. Okay. But Einstein says no. He says that's not the case. He says it doesn't matter whether the train is moving or not. This is wrong. And Einstein says A will also find speed of light to be c. Okay? It's like a big claim. It's not easy to swallow, but that's what it is. So we could go around and argue why he had to do this. There are many reasons, but for the moment we don't care. Let's just say these two postulates are fixing some problems that we are going to talk later. But now let's see what is the consequence, right? If I assume these two postulates, laws of physics are the same in all inertial frames, and speed of light is c in all inertial frames, let's see what this will give us. Good. Any questions? Yes.
John, what was the purpose of publishing and postulating the first postulate, and actually what did Einstein try to set out with it, and how we should relate it?
Yeah, at the moment we don't care, but like he had motivations coming from like electromagnetism, right? Last year you probably have seen that like there are like electric and magnetic fields, and there's something called like Faraday's law, right? Changing magnetic field is going to give like an electric field, and changing electric field is going to give you a magnetic field. And Einstein was thinking about the invariance of these electric and magnetic fields. And when he like studied their invariance in his like famous paper, like electrodynamics of moving bodies, he found so-called Lorentz invariance in the electric and magnetic field equations. He didn't find Newtonian, and he was like puzzled. So he was saying like either Newtonian physics should be correct, or either Newtonian physics should be fixed, or Maxwell equations should be fixed. And he chose to fix Newtonian physics, because Newtonian physics was for smaller speeds. But I think there are details there we don't care at the moment, right? Right now, these two things are all we need. If you accept them at face value, let's see what happens. That's the goal here. Okay, now let's see what happens. So to see the consequence, I want to consider so-called a light clock. I think this is due to Langevin. Probably somebody else, but he popularized it, and he was one of the early defenders of Einstein theory, and he was the one who educated the public about special theory of relativity and its consequences. And it goes something like this. Suppose we take this train. Actually, let me just take a segment of this train. I don't need to draw everything. Suppose this is a segment of the train. And this light clock works like this. So, I don't know. So this is so-called Gedanken experiment, right? You can perform these experiments in real life. But we don't care. We are just like imagining some thought experiment, and we are trying to understand the consequences. And in that Gedanken experiment, this light clock works like this. Light goes from here, reflects perfectly from the ceiling, and when it comes back here, it is like one tick. If you want, this is like 1 nanosecond, something like that. And suppose the length of this train is L naught. So I will try to use subscript naught for the frame of this wagon, and I think for the other one, I am going to use letters without subscripts, if I can be consistent. So now the question is, how long does it take for light to go and come back, right? I can calculate this. T naught, in the sense that this T is measured inside the wagon, and it's going to be like, it can go L naught up, it can come back for L naught. In total is 2 L naught, but the speed is speed of light, so this is the total time. Okay, any questions, any objections? So this is according to observer B. But for observer A, it is going to be a different thing, right? Because this wagon is moving with velocity v. So initially, when the wagon sends the first signal, it's at some position, right? And when it reaches the ceiling, it's going to be in a shifted position because it's moving according to outside observer. And when it comes back and reaches the ground again, it's going to be in a different location again because it keeps moving. So this is according to observer A. And the light, according to observer A, is going to take something like this. The path of light is something like that. So this length is still L naught, and this length, okay, this is, suppose the total time for light to go up and come back is t, then the velocity of the wagon is v. According to observer, what is the length here? So this first half in terms of v and t, v times t over 2, right? Because it's like what we call t is full thing to go up and come back. And the same thing here, v times t over 2. And total length is, we know the Pythagorean theorem, right? Like this length is going to be equal to the square of sum of these sides. So then the total time is going to be equal to L0 squared. Maybe I can just calculate half of total time, which is the same thing. L0 squared plus V squared T squared over 4. And I'll take the square of this entire thing. So this is the length. And if I divide the total length with speed of light, because light is taking this path, I'm going to find the total time, which is T over 2. Okay, and here the key is I am using the same C, because all observers should see the same C. Okay, any questions or comments? So you can see this equation is written in terms of T, so I need to solve it for T, and it is a simple thing to solve. Just take this C squared T squared over 4 is going to be equal to L naught squared plus V squared T squared over 4. And I can combine it. Okay, let me copy this entire thing. I want to move this to this side and put a minus sign. And I want to take it in the parentheses of T squared over 4 so that I can erase this and erase that. And I actually want to take it C squared parentheses too. This is 1 over C squared. And now I find T is going to be L naught divided by maybe 2 because of this 4. 2 L naught divided by C times 1 minus V squared over C squared. Good? Any objections? But in the frame of observer B, we found this to be T naught. So let's relate T naught and T to each other, right? This was like this. But from here, right, this so this piece is T naught, basically. Then T is going to be equal to T naught times 1 over 1 minus V squared over C squared. Simple stuff. We just used high school algebra to find one of the most important things. So here, V is, right, speed of light is the maximum velocity that we can reach. Nothing can be at the speed of light. And V over C is always smaller than 1. 1 minus something smaller than 1 is smaller than 1. 1 over something smaller than 1 is something bigger than 1. We find that T is bigger than T naught. So if we are thinking about the clocks, the same clock ticking inside the train ticks with some rate T naught, but the outside observer which observes T is observing this tick to be a little longer. Okay? That's why we are saying that moving clocks tick slower. And this is what we call time dilation. Okay? Any questions? Yes. Which clock? If the clock is inside the train, right? Suppose there is like a clock inside the train. Exactly. Now I'm going to also mention that. So this is a mutual thing, right? So this clock, we built our problem to be inside the train, right? If the clock was outside, suppose A is measuring his time and B is looking at A, what he is measuring, it's going to be mutual. So let me write that. So this is an important thing. So this effect is mutual. So what this means is like B sees clocks in A frame slower. And A sees B clocks slower. And that's what it should be, because we say that like right, all frames are equivalent. If I see your clock to be slower, and if I'm moving with respect to you, you should see my clocks to be slower, right? Otherwise, things would not be like in the post, like in the all frames would not be equivalent otherwise. Yes.
You said that the square root cannot be negative, but it can be, maybe it can be 0?
Like it can be 0 if v is equal to c, but it cannot be, v can never be equal to c. We are going to see that, right? The wagon can never go with the speed of light. We are going to see towards the end of this chapter. But at the moment, like take this as a postulate. It's the postulate of relativity. Speed of light is the same in all reference frames, and nothing with a mass can go with the speed of light. So this is the postulate. And the second postulate is like laws of physics are the same in all inertial frames. Okay. Yes. So this is not, this is not about light. This is space and time. So we are going to see in a little bit something weird also. So the time in Newtonian mechanics is absolute. Like, right, every single location in space in Newtonian mechanics, we imagine there's like a clock which is absolute, and we measure speed and acceleration, or everything with respect to that. So here we say that this is not the case. Clocks are not absolute. They change from frame to frame. Now, in a little bit, we are going to see meter sticks, right? The measurement we take also are not absolute. They also change. And hopefully, not today, but next week, we are going to see that space and time, they both change, but there is something invariant if you look at things the right way. And it's going to be invariant space-time. So from that, we are going to see that we actually have to unify space and time to make things work in special relativity. So if you want, that's why people say time is kind of like the fourth dimension, because space and time are the same thing. Good. So this is the first thing. So this is the time dilation, but this is not the end of the story. Let's continue. Suppose this clock doesn't work like that, but it works in a different way. Suppose, I need to draw like a smaller train because I have to repeat the train. Suppose my clock works not to the ceiling, right? What is the reason to send it to the ceiling? I can also send it like this. So it goes like that and comes back. And still the train is moving with velocity v with respect to an observer outside. And now I want to call the length, this length L naught. If that confuses you, you can use another letter. I will use L naught to not run out of letters. And the clock time, in this case, exactly like what we said, because inside, for this observer, nothing is moving, right? Light is coming and just going back. It's going to be 2 L naught divided by C. So there's no trick here. But for so this is A, and this is B. This is with respect to B. But according to B, the wagon is moving, right? I have to like have this. So this is when the maybe let me clean the clutter a little bit for you to just see a little bit more clearly. When the light starts on this end, okay, let me just shift it a little bit down. wagon is here, and then later maybe it's going to be like this, and then later it's going to be like that. Okay. So we need to calculate the extra distance, right? So when light leaves from here, right, when the light reaches on this end, the wagon will be shifted a little bit. So A needs to account that too. After the reflection, light moves to the left, wagon moves to the right. So the distance is getting smaller because of the motion. So A also needs to account that. And that's what we are going to do. So I want to calculate two things. Let me call it T1 is, so okay, now, so this light is going. So when it reached the end, the wagon shifted a little bit, right? Now it's going to be here. So let me call this time T1. T1 is going to be equal to L naught plus velocity times T1 divided by speed of light. Now it's going back, but it doesn't have to go back all the way. Once it reaches here, the wagon is shifted, so this is going to be T2. So T2 is going to be, how much did it shift? L naught minus V T2 divided by C. Is that clear? I'm just trying to account how much things move. And now I need to find T1 plus T2 is the total time. So T1 is going to be equal to, so from the solution of this, let me write it like this. T1, 1 minus V over C is equal to L naught. Then T1 is equal to L naught divided by 1 minus V over C. I think I forgot 1C here. I think this should be, oh, this should be L over C. Okay, so this is L over C. And similarly, T2, 1 plus V over C is equal to L naught over C, and T2 is equal to L naught over C divided by 1 plus V over C. Good. But we want to calculate the total time. T without naught is the time according to observer A, is going to be T1 plus T2, and it's going to be equal to L. Actually, according to observer, I also want to change L to L naught to L, because we are trying to see that if the observer is going to see a different length. So this is L, this is L, this is L, and this is L. And this one is going to be L over C, 1 over 1 minus V over C plus 1 over 1 plus V over C. Good. And this one is going to be equal to L over C, 1 plus V over C plus 1 minus V over C, and divide this entire thing. 1 minus V over C times 1 plus V over C is 1 minus V squared over C squared. So these are gone, and I have 2L, right? 1 plus 1 is 2L divided by C, 1 over 1 minus V squared over C squared. Now this is T and this is T naught, but I know how to relate T naught to T, right? So let me just write this thing below. From time dilation, I know the relation between T and T naught. Basically, T should be bigger than T naught by a factor of 1 minus V squared over C squared. So if I put this here, what I'm going to find is so this thing is equal to this thing. But T naught is also determined by what? T naught is determined by 2L0 over C. Okay. Yes. So the T naught is 2L0 over C, right? Now I have a relationship between L naught and L. And let's simplify. This one is gone. This one is gone. And I think L is going to be equal to L naught. So if I take it to this side, it's going to be 1 minus V squared over C squared. Okay. And now, okay, V is less than C. 1, so then V over C is something less than 1. 1 minus something less than 1 is something less than 1. If you take the square root, it's still less than 1. If you multiply L naught with something less than 1, the result will be less than L. So what we see is L is less than L naught. So that's why we are saying that moving sticks get shorter. And that's why, okay, I think the widely used thing is Lorentz contraction. But some people are like historically more sensitive. They are going to say Fitzgerald contraction. Either way, it contracts, and the length of the stick decreases. Okay, 2 key results. So if we take Einstein's postulates to be correct, time, if the clock is moving, it should look slower to us. If the meter stick is moving, it should look shorter to us. I think that's how I remember. Who is getting shorter, who is getting longer? Think about that. Moving clocks get slower, and moving sticks get shorter. Maybe we can take a 5-10 minute break and then continue in the second hour.